Welcome to the first episode of the Innovation Without Boundaries dialogue series from the Wits Innovation Center. I'm Prof Christo Doherty, and in this monthly series, I will be investigating the how and why of what makes a successful innovator. My guest in this first episode is Dr. David Fine, a scientist, inventor, and entrepreneur whose career has spanned continents and disciplines and whose work has quietly shaped the world we live in. Born in Johannesburg, Dr. Fine studied chemistry at Wits University before completing his PhD in combustion chemistry at Leeds and then leading groundbreaking research at MIT. He went on to spend nearly 3 decades as a researcher at Thermoelectron, where his innovations helped pioneer airport sniffer devices for explosives detection and the advanced forensic tools that contributed to solving the Lockerbie bombing. Meanwhile, his discoveries on the carcinogens known as nitrosamines improved global food safety standards. As an entrepreneur, Dr. Fine founded Biterra, developing landmine detection technology, and later Vero Biotech, which created the inhaled nitric oxide therapies for treating pulmonary hypertension. Holder of over 100 US patents and recipient of an honorary doctorate in science from Wits University, Dr. Fine exemplifies how curiosity, persistence, and innovation can save lives and reshape industries. It is a great honor to launch the Innovation Without Boundaries series with Dr. David Fine as my guest.
David, it's a great honor to have you here as the first guest in our new WIC podcast series, Innovation Without Boundaries. So welcome and thank you for
Thank you.
making it. And let's kick off with the first question. And what was it in your education and early career that empowered you to become such a scientific innovator?
Uh, Probably on my unusual background, and let me go into that in detail. At Wits, I did chemistry as a major, as you know, for a BS degree, BS honors degree. But I also majored in for 2 years in physics and maths and applied maths. So I have a very strong physics background. At Leeds, when I did my PhD, I landed up in combustion and explosion chemistry. And that required me to study fluid dynamics, heat transfer, mass transfer, uh, thermodynamics. I got into bond energies of how molecules break apart and can release energy exothermically. Um, Something else that I learned from my professor there, Peter Gray, was if you know you're right, don't concede anything. If you've done the data and you know your facts and you've got data to back you up, don't concede that you're wrong on anything. You know your stuff better than anyone else. Um, in Canada, I went through an experience where I was fired as a postdoc. I was had done a postdoc in England. I went to Canada to do a postdoc in Winnipeg at the University of Manitoba, and I was asked to do something which it was the pumping speed on a mass spectrometer. The professor wanted to go to narrow bore tubing, thinking that wide bore tubing was just a waste of time, and he could go much faster if he went to narrow bore. Complete opposite of what fluid dynamics teaches you. I refused to do it, and I even demonstrated to him that it wouldn't work, and I got fired. And here I was in Canada, not knowing anybody, with a wife and a 2-year-old and another one on the way. And I got out of that. I landed up as a faculty member at MIT.
Mm.
I took the letter when I got an interview there. I took the letter with me and showed them what he wanted to do. I'd never heard of MIT before, coming from South Africa. Certainly at that time, we didn't know what MIT was. I was at the interview. I was pretty critical of some of their ongoing work, which probably they'd never experienced because an American would have been in awe of MIT. And anyway, I got the position. And there's a fortuitous situation. At MIT, I studied combustion. I was the manager of the combustion lab. I learnt all about oil and gas and coal and even garbage. Uh, it was the time of just discovering how important air pollution was, nitric oxide formation, and I built an instrument to detect NO. So I had this very broad technical background, and probably very importantly, I had developed what has now been called grit, the tenacity to finish what you start. It's hard, and there's an excellent book by Duckworth on called Grit, which is an excellent predictor she's found of people who going to succeed as opposed to academic merit. So uh, those are the uh, backgrounds and the broadness that gave me the ability, I think, to be able to innovate because I could land on my feet in many different fields and be comfortable.
So tenacity is a very important ingredient in the personality mix that makes for a successful scientific entrepreneur. Looking back, maybe deeper into your childhood and education, what other experience contributed to you becoming such a successful scientific entrepreneur?
Um, there's several things. Acceptance of failure. Um, when I was 8, I'd gone to a birthday party at a friend of mine who then developed mumps. I got mumps, my brother got mumps, and with mumps, my 2-year-old brother got encephalitis, swelling in the brain, and he was totally mentally retarded after that. My mother could never overcome that, and she all my life I was blamed for my brother's illness, and it was something that was um, that failure and overcoming the failure was very, very important, and you learn so much from that sort of failure. I remember at school I failed first grade. I was a very poor student, and it took the when Sputnik went up, the first Sputnik. I was a junior at high school, and suddenly I became interested in science, and my E's and F's in science became A's overnight. And it was just chance things like that. I suddenly had an interest. And whereas before that, I was considered the dunce, the failure, and suddenly I got a distinction in science and for matric, and and so I went to Wits and I studied chemistry, physics, maths, and applied maths, and it was. Uh, I think those are the key things in my early background that drove me to science.
I'm really struck by the influence of the Sputnik. It was that Russian satellite that prompted the whole American military industrial focus on space travel. And President Kennedy, with his 1961 declaration that the USA would put a man on the moon within the decade. How did you as a teenager in South Africa experience the Sputnik? Was it broadcast on radio?
It was on radio, and the Sputniks came over Johannesburg, and and on the radio they were broadcasting the beep 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 of it. And I remember at night turning all the lights off and going to somewhere very dark and trying to see it. You couldn't, but hearing this, it was just fascinating. It just suddenly I thought, wow, look at this. This is just incredible. And it just inspired me into uh, being complacent and studying English and history and Afrikaans and all the different subjects we learned. And suddenly I got an interest in science. And it was coupled with having a brilliant science teacher, Mr. Corbett, who then became the principal of the school later on at King Edward's. And it just inspired me into gee, this is what I want to do. This is science. This is fabulous.
Following on from that, David, you've spoken frequently, notably in your address at Wits when you awarded your honorary doctorate. You've spoken about the beginner's mind and chance as catalysts sparking innovation. Could you share a pivotal moment in your own career when unexpected detours led to research breakthroughs?
Um, Let me start with a chance, which is so important. Uh, I went to Leeds to study nuclear chemistry. I had a scholarship there. When I got there, I was told, "Oh, the professor I was going to study is was leaving." He told me he was leaving and going to be a chancellor at Nottingham University, and I landed up looking at doing a PhD in explosion chemistry and combustion. Uh, Pure chance. Uh, these are things that sort of just happen. When I came to after I'd left MIT, I was working at Thermo Electron, a small R&D company in those days, and I was hired to work on thermionic energy conversion, high temperature heating a metal across a vacuum space to generate electric power. And one day at lunch, a visitor came by and told me about nitrosamines and how important they were as carcinogens. I didn't even know what he was talking about. He drew a formula, and I just looked at the formula and wow, I knew how to measure these. And this was the biggest issue in the field at the time. Pure chance. Those sort of things just happen because you just happen to be the right person at the right time. But the beginner's mind is so critical. When I looked at that NO formula, I didn't know what a carcinogen was. They had to explain it to me. I didn't know what carcinogenesis was. I had no history whatsoever of the analytical chemistry of nitrosamines or how to detect them. I just looked at the molecule and said, oh, you detect it this way. If I was an expert in the field, they were battling trying to find a way to detect it. They didn't understand it had a very weak bond. I knew that from my explosion chemistry. And it was just obvious to me. It fell out. But if I had not uh, been that naive, people in the field just couldn't take their blinkers off because everywhere they turned, they were thinking of, oh, you can't go this way, you can't do this, you can't do that. And even when I presented it at an international meeting, there was no one in the audience who understood a word I was saying. And so it's things like that. Another example of just staying with nitrosamines for a moment. Um, we did an experiment where we took some blood from the arm after we'd just eaten a bacon sandwich and washed it down. The colleague washed it down with a beer. And we found the nitrosamine levels went up and down. And this was kind of expected. Bacon is a potential source of nitrosamines. I didn't know that it was well established in the field that one pass through the liver and low level nitrosamines or any carcinogen is metabolized. That's what the liver does. Here we were finding it. The flag I caught from that was unbelievable. Uh, One person tried to duplicate it, didn't have the beer, a person in Germany, and suddenly the field realized, wait, the alcohol is important here. The alcohol was overwhelming the liver, and the carcinogen could get through to the target organ. All the workers who worked with that with me at the time in Germany and the UK have since died, but it's coming very much back in the current climate where alcohol is now considered a carcinogen, and people are being told, you know, don't even light drinkers are there's a higher incidence of cancer. Yet alcohol is not a carcinogen. You can feed as much as you want to animals, any animal species, they don't get cancer. Um, it's going back to this very old issue we worked on that was by pure chance. Uh, the discovery that the nitrosamines were in the blood with alcohol, but not if you didn't drink alcohol, it wasn't there. That's probably the explanation for why alcohol is a carcinogen. And I'm trying to work here in the U.S. with some physicians to go back and relook at that because those papers. One of the paper was published in Nature. They were, it was very much the field at the time. Um, in the explosion area, one of the key things that happened was people thought the way to detect everything was by a chemical was by sniffing vapor. When I started to build a detector sensitive enough, I found I was detecting RDX and PTN explosives, which the vapor pressure was so low, there was no way I could be detecting it. And what was going on? And I slowly began to realize, based on the size of the peaks, that we were detecting nanogram quantities, nanogram particles, essentially. And it was a time when nanoparticles were unheard of. This was a breakthrough in thinking, which took me many years to understand. But at the time, the field was all focused on vapor. Yet I was finding explosives very readily. A fingerprint. Someone, if I picked up a piece of explosive and put it down, it was on my fingers. If I touched a piece of paper, I could pick it off that. If I shook hands with someone, it was on their hands. And this led me into the whole world of explosive detection in an area which just had no one else was thinking in those lines. The uh, was is that now, but it was just being a beginner. Um, I think the expert is so embroiled and buried in their own expertise that they can't think of things that other people may have done wrong in the history, and it's become accepted fact for them. And they can't really innovate. A person who joins that group, who's, say, a young student who doesn't know better, or someone like myself who's prepared to go into a field that I know nothing about, uh, you can bring a different discipline and very often solve a problem. Whereas the expert just can't find a solution. And I found this again and again to be the case that I thrived when I was a newcomer, naive, didn't know what I was doing in a field with a lot of experts. And it very often it allowed you to crack the problem because you didn't have their background, you didn't have their baggage, you didn't know about what other people had thought. And what typically happens is something was misinterpreted, something was done differently, and you break through that uh, with that naive um, uh, thinking, and, and and the experts, of course, get very upset with that, but they eventually come around. But it's that unexpected situation that comes from that.
That insight into explosives detection that you developed into a fully fledged company that was Cyterra.
Well, I'll talk about that process. The um, I was at Thermal Electron when I did the bomb detection work, and that was all done at Thermal Electron. And one of the things we did was started to realize, gee, I had the sensitivity to sniff TNT, which is a much higher vapor pressure than the plastic explosives. And there's an impurity in it called DNT, dinitrotoluene, which is much higher vapor pressure. And I built a little detector with a response time of under a second, and man, we could find TNT. We took it to a minefield, an army minefield, and sure, we could find TNT, but it wasn't above the mine. It was to the side of the mine because the vapor took the path of least resistance to the surface based on topography, a root, a rock, or something. It would have been a terrible mine detector. You would have killed killed the people because the where the mine was the plume was somewhere else from the mine. It could be 6 inches a foot away. That made me realize that this is a failure. What what the lesson I learned was I had to see in the ground. And at that time, cell phones were just coming into play. And a cell phone I can hear you inside a building. You've obviously at that frequency, you can penetrate through rock and brick and glass. Maybe you can penetrate a few inches into the ground where the mine's buried. And I teamed up with a group with the expertise in ground penetrating radar. And we then I left Some Electron and formed a company, Cytera. And we did just that. And that became the U.S. Army Marines mine detector. It was deployed just in time for Iraq, the American invasion of Iraq and Afghanistan. And we could not only find the mines at walking speed, we could identify the mine and which model it was from the shape and the metal. There was a metal detector as well, and that just changed mine detection. Uh, but being able to see and receive a signal inside a building got us into another area of interest, and that was finding a person inside a building for a military application, because that's where the funding was. Uh, Before you break down the door to go into a building, are there people inside? Where are they? Well, if you can receive a cell phone inside, you can start to do a Doppler radar and pick up the heartbeat of the person. So you know where the person is inside the building, and we developed into something the size of a cell phone. Just hold it up to the building, and you could tell where the people were, if there were people. Uh, you know, it they were fun, very much fun projects, totally different from chemistry. But uh, I wasn't the radar expert, but the people I teamed with were, and jointly we were able to make this all happen in a very, very short time frame.
When you develop new working prototypes or you propose solutions to problems that had stymied experts, what was the response of the experts? How did they respond to you with your beginner's mind?
There were two different kinds of experts. If the expert had come to me with a problem and I solved it, they were thrilled. Let me give you sort of two examples. A sister group when I was at Thermo Electron had developed a air pollution monitor for sulfur dioxide, and it was based on pulse fluorescence, UV pulse fluorescence, and it had been approved by EPA. And while they were doing final testing, they found that a diesel truck going by spewing smoke gave sharp spikes, and EPA was embarrassed. The company was going to have to recall the instruments. It was a huge problem, and these people were working through the night. I had lunch with them. They were bleary-eyed, working through the night, and they told me of their problem. And I said, "Well, gee, I'm working on the opposite problem. I'm trying to get more and more sensitivity so I can find nitrosamines and explosives. Why don't I make you the worst possible gas chromatographic column and flatten out your peaks?" Today, you would solve the problem with high-speed electronic software, but then you had to do it another way. And we joked about it, and I said I was serious, and went to the lab afterwards and made them the worst possible GC column I could make to capture the sharp peak and slow it down and let it leak out so it was no bigger than the thickness of the baseline, because the data was all being recorded on graphically. And to my surprise and their surprise, it solved the problem. Well, they were thankful as you can imagine. I mean, this I'd solved a problem for them. I mean, I was a hero. Uh, Another area like that was the Coca-Cola company had introduced, and the beverage industry in general had reduced returnable plastic bottles. And the plastic bottles had a problem where they absorbed contaminants. So they had to make sure the bottle had not been exposed to a pesticide or gasoline or something else. And one of the problems they had, and I got to meet them by chance, but uh, we had high speed instruments that could detect things in real time, but sampling was a real problem. The beverage industry was sampling by the opposite of a filling machine, where it comes into a huge turret machine costing about $1 million. It grabs a bottle, puts a probe inside, sucks it out, and it chugs around while they do their analysis, and then puts it back on the line. Empty bottle is very unstable. It had to be very precise, very expensive. And I came back from the visit. I'd never been inside a beverage plant. And one night I'm washing the dishes and I opened the water faucet water tap too hard. Water shot into a cup with some coffee in it and sprayed in my face. Wow, I solved the problem. What you need to do is just lean over the bottles and blow air in. And a space of a bottle later, the air you've blown in is going to be going up. It's got to go somewhere, and sample that air. So we got rid of the entire machine, the entire sampling machine, and that led to multi-$100 million business for Thermoelectron. Uh, they were thrilled. Then, if you get into, say, the nitrosamine field, they just flatly did not believe me. I went to an international meeting in France, in Lyon, and I said I could measure nitrosamines. And they thought it was a joke. In fact, I had a lot of trouble defending my paper. They wanted to take it out of the proceedings because it was obviously such garbage. They did a round robin study then where they sent samples of canned meat to any lab in the world to analyze, and they'd spiked them with different nitrosamines at different levels. About 6 cans. We participated. I didn't know anything about analysis at that time. We found that the existing methods didn't work. So we developed a method where we added a mineral oil and distilled it out of the oil. And we tested it with some luncheon meat and got it to work and submitted our data. And about a month later, I get a phone call from Leon, an Englishman working at IRAC, hopping, screaming, mad at me, calling me a miserable, cheating, lying bastard. Who did I bribe in Leon to give them in the codes? No one in the world had been able to tell which can had nitrosamines. We had told them which can, we had told them which nitrosamines, and we had told them exactly how much within experimental error. They just refused to believe it. I finally got him, when he came to the US next, to come and visit our lab where there's only one of our machine that I developed, and bring his own cans, but don't tell anybody this time. Because they were doing a police audit in Lyon about who had leaked this information to us. And he repeated it himself. And that was the way we got over that hurdle. And suddenly, the National Cancer Institute bought 10 of those machines. They distributed to the major labs around the world. And suddenly we were the established experts. But the initial reaction in a new field was fury. In the explosive field, when I was suggesting particles and showing we could detect explosives in suitcases, etc., the funding agencies who were the experts um, were they just were lying. We're cheating. It's not possible. And we had a small amount of funding. They didn't increase it. They were going to other places. And I told them about particles, and they just said that's garbage. It's nonsense. No one ever's heard of particles as being detection. You're we they got one of our instruments, they put it in their own labs, and they called it a random signal generator. Every time they tested it, it was randomly analyzing and calling 10 different explosives. Their labs were hopelessly contaminated was the reason. And this carried on, and it got very serious. I was accused of being in league with the terrorists. I had an FBI investigation of me on one occasion, triggered by some of the stuff, for giving classified information. It was bizarre. After Lockerbie and the bombing of a Pan Am flight, um, the British used our technology, our technique, to find the explosive. It was PTN, and RDX, it was Semtex, and they still refused to believe it. They ran a test with our equipment on luggage, and they refused to analyze for trace. They had a sniff. I told them, no, that's not how the machine works. You got to wipe the surface, the handles of a suitcase, and then analyze it because there'll be particles there. They refused. It took a congressional inquiry into Pan Am disaster for them to realize that uh, this was nonsense, and the people got fired. New people came in and did a proper test, and they asked what they should do. I said, get some clean trailers, don't go near your labs, they're contaminated. Check everybody who's going to work in it that they're not contaminated. They've got to wear gloves and clean clothing, and now do it. And it worked. And suddenly we were heroes. I've got a plaque in my office about, I'm one of the pioneers of trace detection, and thanking me for my work. I've got letters from them. I've also got letters from the previous FAA people who were calling me all these names. So the reaction of your experts is, particularly with egos, and they all have egos, is they go nuts. They just can't handle the fact that someone has come out of the blue and told them uh, that they're doing it all wrong. And as I read the literature, the discovery of, say, the how ulcers are formed from a bacterium and not stress, which only came about in the late 80s. Similar thing happens in all fields. Someone comes up with a brand new idea and it's contrary to what the teachings are of modern medicine. People just refuse to believe it until someone does a dramatic experiment. In that case, they had to show that they had no ulcers, swallow some of the bacterium, 2 weeks later having the ulcers, and then curing the ulcers with a antibiotic. I mean, I developed ulcers about 15 years ago. One dose of antibiotics, and they were gone. Yet in the late as the 1990s, ulcers were a major problem. So I think the answer to that is, if you're going into a field and there are experts there and they haven't asked you to solve something, and you're just going because you've got some ideas or you've got a new presentation. If it's working, they call you a charlatan, a cheat, a liar. If you've got ideas, they think you're nuts. Uh, it can be very difficult, and it takes, another part of innovation is to be able to withstand that criticism. A lot of my colleagues and my friends, when they went into new areas, they were so devastated by the attacks. It's just very difficult. It- Tenacity and the grit, and if you know you're right, just stay with it. For explosives, it took from 1975 to 2000, 25 years before we were accepted. And one thing I still feel strongly about is the whole Lockerbie bomb and the deaths and the students who are coming back from a break from studying in the UK, who were killed. That should not have happened. We had the technology, and you know at every airport today, if they when they X-ray or they see something, they'll swipe. They'll take a wipe. that's the technology we developed. But at the time, it was, it takes a battle. And I'm sure that's true in any field. As I read about other people in other fields, the same thing happens again and again.
David, just to stay with this beginner's mind, you've changed fields many times through your career, often quite drastically. How do you navigate across disciplines, and what lessons do you carry from one field to another?
Um, what I've always done is I haven't set in the back of my mind that I want to do something long term. I want to study this. I want to be a doctor. I want to do that. I sort of let the data lead me. So I don't have preconceived views on things. So let me walk you through some of that. I'd studied combustion for my PhD, and I was working on it at MIT. And I then measured, I was looking at NO as a pollutant, nitric oxide. Nitric oxide's a unique molecule. It's got a lone electron in the outer orbitals, a very two-atom molecule. So it's both a stable molecule and a free radical at the same time. Weird molecule. There's nothing else like it that's naturally occurring. Um, Knowing that, when I stumbled into the nitrosamine field, where an expert, someone who'd written a book, The Politics of Cancer, Sam Epstein, over lunch told me about nitrosamines and how bad they were, and he drew a formula for me, and for me, it was obvious what the solution was, and developed an instrument. Uh, it was, okay, now I'm in a nitrosamine field. Uh, I suddenly found I was an analytical chemist doing ultra trace analysis. We one experiment we did was with alcohol and uh, having alcohol with baconite, which I'd mentioned. But then I started to think, well, if I can do NO, what about NO2? If I just heat the NO2 a little bit, it'll break down to NO. So why don't I raise the temperature of my pyrolysis machine? And I had an explosive detector. Oh, now I can do explosives. Uh, Gee, that's interesting. Maybe can I do TNT? Yeah, you can do TNT very well. It's got a much higher vapor pressure than plastics. Oh, I can do mines. Well, no, you can't do mines. Mines, no, the vapor plume isn't above the mine. So I went to radar, and then went to through all radar. Um, an ICBM, intercontinental ballistic missile, in in Arkansas blew up in the silo when a crewman dropped a wrench and punctured the side, and there was a leak of the rocket fuel. The rocket fuel was hydrazine and N2O4, and we easily won the contract to detect that because that's what we'd been doing with nitrosamines. And I got to climb into a silo and go in the launch gantries at Kennedy and Vandenberg. No, fascinating stuff for a chemist to be doing. Um, and I got to work with N2O4, the oxidizer, dinitrogen tetroxide, highly toxic. The While I was just thinking about this and carrying on with my work, it was suddenly acknowledged that NO was a drug. Other people had found and won the Nobel Prize for showing NO could dilate blood vessels and relieve hypertension. Wow, that's interesting. This molecule that I've been working with, and I probably knew more about the chemistry of NO by then and converting things into NO and from NO back and forth. Wow, I dived into that. What's going on here? Uh, and when I when I sold Cytera, and I started the work at Cytera, I started a pharmaceutical company. Oh, I can let's see what I can do here. N2O4 is a liquid. They were delivering NO, and they still, majority of is still with from a gas bottle, 800 parts per million in nitrogen. That's a huge tank that's tall as a man, weighing many hundreds of pounds, 100 pounds of NO in this big tank. Well, let's see now. Half a cc of N2O4, that's um, uh, each molecule gives 2 molecules of NO2. I can change that to NO. Instead of 800 parts per million, it's pure. That's a factor of 1,000. It's a liquid, not a gas, another 1,000. And suddenly I'm 2 million times smaller in size and weight and mass. I got something that's wearable, that can deliver the same product. Um, how do I deliver it? If I've got water in a kettle and I boil it, the vapor comes out, the steam comes out, and it's just at boiling point steam until the last drop of water is evaporated. So if I heat this N2O4, it'll come off as NO2, it'll break down, and I can convert the NO2 into NO. Uh, and as long as I keep I know what the temperature is. That'll be my rate of heating. What my concentration is. I can. I've got a tiny little NO generator. How do I convert it? The obvious way is what Linus Pauling taught us about vitamin C. I'd been to a lecture of Linus Pauling's, in fact, and so I was there as a guest a long time ago. Edward Teller, the founder of the hydrogen bomb, was a advisor to Electron, and he and I often got to talk because he knew I had a background in explosives now. And when Linus Pauling won an award, Edward asked me to go in his place. So I was a guest of honor at this thing, and I got to meet Linus Pauling. And I thought, gee, just pass the NO2 over ascorbic acid in the right form, and I've got NO. It worked fine. Um, so that led to uh, what is now called Vero. Initially, it was called Geno, an FDA approval. In typical fashion, even colleagues of mine said, "Are you crazy? You can't put into a 4 near a patient. Uh, it's you'll kill somebody. I mean, this is dangerous stuff." Well, we made it so much safer than a gas bottle that FDA had no problem approving it. But each discovery that went through there builds on the previous one. You do something, you learn, you go to the next stage. You build something, you learn, you go to the next stage. That N2O4 generator I described built on my semionic background, on where I came to thermoelectron to heat a tiny vessel to generate electric power from heat, and just following where those leads came from. I didn't decide I'm going to go into um, mine detection or through wall radar or this or that. It was, where's this where's this leading me? What's it telling me what to do?
There seems to be a strong element of play in the way that you've approached this problem.
It's always, if it's not fun, I don't do it. It's got to be fun. You got to want to wake up in the morning and be dying to go to work. In fact, I that's a very important issue. When I was in the nitrosamine field, and um, I realized that I'd been in it for 10 years, and at that time I was one of the leaders in the field. Uh, the amount of nitrosamines that were formed that were present in the environment could account for a few thousand cancers, but not a major source of human cancer. The non-volatile ones were going to be much more important, and I was getting bored because we were discovering nitrosamines in different things, and in cosmetics and all this different kind of things, and rocket fuel and other stuff. And I decided I'm going to walk away from this. This was boring. I was the expert and I had all the prestige and I was invited to the international meetings and I was advisor and to even the German government, the US government. I was giving congressional testimony, but it was boring. I wanted to have fun. And so I intentionally got out of those fields. And most people I know cannot understand why I did that. And it was just, I wasn't having fun. I wanted, it's got to be enjoyable. You've got to look forward to getting up in the morning.
David, to get some concluding thoughts from you, you of course received an honorary doctorate in science from Wits University, and you established the Angela and David Fine Chair of Innovation, which I'm the very appreciative acting incumbent. And you've also donated to Leeds University, where you did your PhD. You've demonstrated a strong commitment to educating future scientists. What advice would you give to a new researcher in order to make the advances that we need at the intersection of science, society, and innovation? What would you say to young researchers working in science, aiming to get their PhDs and then look for a postdoc position? What would you say to them now in the 21st century?
I'd say there are four things to think of, and it's not only scientists. It could be in the medical field, engineering, architecture, uh, business. I mean, it could apply across the field. Diversity is a very powerful one, particularly in South Africa, where you have such a diversity in upbringing, culture, lifestyle. Someone brought up on a farm learns to do things that are so different than someone brought up in Johannesburg or New York City. In the farm, you're worried about your tractor, you're worried about when you plant, things like this, milking the cows every day. In New York City, you worry about the rush hour traffic and where to get your cup of coffee sort of thing. Um, the diversity of culture is enormous. The diversity of upbringing is enormous. Uh, Diversity of work you've done, a scientist, a cook, an accountant, a teacher, um, a taxi driver, uh, an engineer, all are trained to think differently. Put several of them together and you say, here's a problem, solve it. They'll let you think of it differently. If you can hear those interactions and they talk to each other and recognize that and you've got to have people who prepare to do that. I've often found I can break through and solve problems because you've got people who really want to help you solve this thing. And with that diversity of people who are thoughtful, they've got to have some training in thinking, like a scientist or something like that, or accountant, whatever it is. But uh, man, is that powerful? That diversity of thinking, culture, and probably South Africa is one of the places with more diversity than almost any other place in the world. And so there's a lot of power potentially there that's going to come out of this diversity. And not only South Africa, but the rest of Africa. It's so different. The way of life and everything they've done is so different than what people are doing, say in America or China or uh, people who grow up on an island in the South Pacific. They they think very differently than a South African, and it's I think diversity is very important. Another one of enormous importance is grit. Uh, First of all, be sure of your facts. As an innovator, don't jump before you're sure. Make sure it's repeatable. Make sure other people can repeat it. Then don't stick your neck out until you've done that. Then don't give up. Just stay with it. You're right. You'll get criticism thrown at you unbelievably. And when that criticism comes, and this is another one, when the criticism comes, remember people attack you personally because they've run out of technical arguments. Their ego is now kicked in. The expert who calls you an idiot, calls you a moron, calls you a charlatan. Why is he doing that? Not because he's got technical arguments. He's protecting his ego, and you've got to recognize that you're fighting his ego. Not if he's got technical arguments, you can answer them. But when he calls you all different names and tries to eliminate your funding or whatever it is, get you fired. I found after a while that when someone called me a cheat, it'll never work, an idiot, that was music to my ears. I knew I'd solved the problem. And don't give up at that point. That's when you're winning. When they're resorting to personal attacks, uh, and you got to recognize that. So don't give up at that point. Another important one is failure. There's there's no better teacher of anything than failure. You go when if something fails, you got to ask why. Why did my what went wrong with my thinking? What did I do wrong? If you're not failing, you're not at the forefront of your thinking. Um, uh, in I found in scientists that two types of scientists: those that move along steadily, terrified of failure, so they publish a lot, they accepted world experts, but they're terrified of failure. They can't innovate. What I would do when I was managing scientists, uh, I'd call people in my office for their annual review, and if someone they're very proud, they've done everything they've done has worked, I'd say, you can't innovate. You're a terrible innovator. You're maybe a good scientist and you can do things, but as far as I'm concerned, you're a good technician. You're not an innovator. Now, if you don't go to the edge of knowledge and take chances, you're going to be fired. And I did that on several occasions, and the people I did it to both became university professors, and they've done very well, but they haven't innovated. There's just two different, almost different paths. And I remember the shock on some people's faces when I said to them, everything you've done has worked. That's terrible. You've got to be on the forefront. You've got to be thinking just beyond accepted knowledge and stretch. And if it fails, and it will, half the time or some of the time, learn from the failure. Now you're making progress. That's a very important thing. It's sometimes difficult to do when you're working for a company because people don't like failure. But I found it critical and the people around me became great innovators on themselves because they were accepting of this and accepting of the lessons learned from it. Sort of, I remember reading a quote of Thomas Edison. He said, "I've not failed 100 times to make a light bulb. 1,000 times," he said. "I've not failed 1,000 times to make a light bulb. I have successfully discovered 1,000 ways not to make a light bulb." Uh, Failure's okay. Don't do the same failure twice. That's something totally different. But if you're at the forefront of it, could be any field. If it fails, why did it fail? Okay, I can't do that again. This is the lesson it's taught me. Very, very powerful.
That's really inspiring. And David, can you reflect on the university as an environment for innovation? What could universities do to make their environment more conducive to young innovators?
One big thing I found, at least in the American universities, was promotion and tenure comes from your own department. So it was considered a waste of time to work with faculty from another department. That's really bad. But for someone like myself who wants to jump around and just go where it's whatever's teaching me, I want to go from chemistry to radar to whatever the physics, whatever it is. If I'm not allowed to do that, that's shutting me down. I think the universities and the tenure track and say Wits, you've got to encourage people to work across disciplines. Get that physicist, chemist, biologist, whatever it is, together in the same room, and you give them a problem to solve, and let them solve it together. And the solution could be in any of their fields. But if one of them tries to solve it, you're handicapped. Why do you want to tie their hands behind their back? That's one big thing I found in academia. And found it frustrating when I joined Some Electron, founded by former MIT professor George Atsopoulos, who I got to know very well. Um, he, I was in a research department working on semionic energy, but if I had ideas, I could write proposals and get them funded. It didn't matter what the field was. I came in to work on energy, and I landed up doing nitrosamines and bomb detection. He was thrilled. Uh, be, I don't think you can do that at many universities. If you go into a university and you're working on high energy, what the hell are you doing carcinogenesis for? And I think you've got to give that freedom. The other thing it stimulates is the innovators get together. Someone could be developing, this is at Some Electron, an artificial heart, a steam engine to power an automobile funded by the Ford Motor Company. Uh, you know, crazy different innovative concepts, and you're at lunch with these people talking to them or in meetings. They all come at the same problem so differently. It's very stimulating, and universities should be the same. Probably in the faculty lounge it was at least when I was at MIT, but on a day-to-day working level it was frowned upon. Don't do that. I was told, don't work with that people. It's going to hurt you. And I hope Wits has found a way to get around that. It's going to be your problem.
Yes, absolutely. Your emphasis on the strength of diversity here in South Africa, our rich mixture of experiences and cultures, together with your great stress on interdisciplinarity, are for me the two very strong takeaways from this conversation. And I believe that you're actually going to be at Wits this November, where you'll be giving the keynote address at a major chemistry conference.
Yes, it's a meeting of the South African Chemical Society, I think. Plus, some people from Leeds will be there at the same time. Yeah, that encouragement of one of the reasons I got Leeds and Wits together was for this diversity reason. People in South Africa face different problems than those in Europe, say in Leeds. People in Leeds don't even know what the problems are in South Africa. Well, get those people together and have the people from the UK understand a South African problem, and the people in South Africa understand a problem in the UK. And it's my belief unique solutions are going to fall out of that, and encourage those interactions. And I want to see. Obviously, I'm hoping to see the results of that, but I think that's what's going to happen. And I'm putting my money where my mouth is. I think that's going to happen.
David, it's been wonderful talking to you and learning from your extensive experience as an innovator. We hope you can make it here in November.